Hello, welcome. In this short video, we're going to talk about fixed point numbers. This video involves some math, and feel free to pause the video if you need more time. A fixed point real number has a fixed number of bits for the integer part and also a fixed number of bits for the fractional part. We often use the Q notation to describe fixed point numbers. We have UQ for unsigned fixed point and Q for signed fixed point. Each format has two parameters, m and n, where n is the number of binary bits in the fractional part. The definition of m in UQ and Q are different. In unsigned fixed point, UQ, m is the number of binary bits in the integer part. However, in the signed fixed point Q, m is the number of binary bits in the integer part excluding the signed bit. As with integer 2's complement notation, the signed bit is always the leftmost bit. Pay attention, in some literature, the signed bit is also included in the integer part, and thus the total number of binary bits is m plus n. And here, we don't include the signed bit in the integer part, and thus the total number of bits for QMN is m plus n plus 1. Let me show you an example to convert a fixed point UQ53 to a floating point. In this example, the unsigned fixed point number has 5 integer bits and 3 fractional bits. We can directly calculate its value by adding different terms of powers of 2. This after the radius point represents negative powers of 2. We can take a simple approach to convert to float. We simply treat the fixed point number as it were an integer. In other words, we remove the radius point. Then, we divide the integer by 2 to the power of 3. In general, we divide the integer by 2 to the power of n for a fixed point with n fractional bits. Here is another example that converts signed fixed point Q43 to float. The conversion process is very similar to the previous one. We can obtain the results by adding different powers of 2, or by treating it as a signed integer represented in 2's complement, and then dividing the signed integer by 2 to the power of 3. Now, let me show you how to convert a floating point number to fixed point. Suppose the number of fractional bits is n. The conversion process takes 2 steps. First, multiply the floating point number by 2 to the power of n. Second, round the results to the nearest integer. For example, suppose we need to convert pi to the fixed point format UQ 4.12. First, multiply it with 2 to the power of 12, and then round product to the nearest integer. Convert to binary. Add 2 zeros at the very beginning to make the total number of binary bits 16. This conversion introduces a representation error, and it can be calculated in this way. Here is another example that converts negative pi to the signed fixed point format Q312. Similarly, it involves 2 major steps. Multiply it with 2 to the power of 12, and then round the product to the nearest integer. The final result is represented in 2's complement. In the previous slides, we have talked what fixed point numbers are and how to obtain fixed point representations. However, we have not answered a very important question yet. Why do we need fixed point in embedded system? Compared with fixed point, floating point has several advantages. For example, floating point can represent a much wider range of numbers. In addition, with FPU or standard library support, it's easier to program floating point operations, and that the software development time is shorter. Then, why do we still need fixed point? There are 3 important reasons. The first reason is to reduce the product cost. Many microcontrollers don't have FPU in order to save cost. and it's too slow to use runtime software library to make floating point calculations. Fortunately, if FPU is not present and the data range is not very large, we recommend to use fixed point operations. This is because fixed point arithmetic can be efficiently implemented by using standard integer operations. The second reason is that, although fixed point typically has a very limited dynamic range, fixed point has more bits for precision compared with floating point with the same bit length. Third, fixed point is helpful to achieve high performance in many digital signal processing applications. Fixed point has been widely used in many video or audio DSP applications. I will give you more explanation later in this video. Let me use a simplified 5-bit IEEE 754-like floating point to illustrate the trade-off between the representation range and the precision. On this axis, all dots are numbers that can be represented by this 5-bit IEEE 754-like format. As we can see, representable floating point numbers are denser at the smaller end. The gap between two consecutive numbers increases as the magnitude gets larger. The precision is defined as the difference between two neighbor numbers. For floating point, the precision decreases as the magnitude increases. For fixed point, representable numbers are evenly distributed in the representation range. Therefore, its precision is a constant. In general, fixed point provides higher precision compared with floating point with the same number of bits. Adding or subtracting two fixed numbers with the same format can be simply implemented by using standard integer instructions, add or subtract. We can simply treat them as integers and add or subtract them directly. Intuitively, this makes sense, since both fixed point numbers have the same format. The radix points are at the same location, and these two numbers are perfectly aligned. Therefore, we can directly add or subtract them. In the previous slides, I've shown that fixed point addition and subtraction work exactly like their integer counterpart. Based on this observation, fixed point can be used to efficiently speed up DSP applications. For example, if each fixed point number is represented by using 8-bit, a single register can hold 4 fixed point numbers. We can use S at 8 or U at 8 to add 4 pairs of signed or unsigned fixed point numbers in one clock cycle. Such instructions are called single instruction multiple data, SIMD, which perform the same operation on multiple data operands concurrently. Here are two SIMD instructions that add 2 pairs of 16-bit fixed point numbers concurrently. Cortex-M4 supports many other SIMD instructions. Here I present a few of them to show you the motivation why fixed point is widely used in DSP applications. Now, let's see how we multiply two fixed point numbers. For simplicity, we assume each fixed point number has 32-bit totally, with 16 fractional bits. If we multiply two 32-bit integers, the product can be as large as 64 bits. However, for fixed point multiplication, it's often that we need to limit the product to 32-bit. Thus, which out of these 64-bit should be our final result? The answer is that we should remove the leading 16-bit and also the trailing 16-bit, and only keep the middle 32-bit as the final result. Let me explain the math behind it. For fixed point numbers FA, FB, and FC, assume their corresponding integer is IA, IB, and IC respectively. The integer is directly obtained by removing the radix point from the fixed point. We know that a fixed point number equals its corresponding integer divided by 2 to the power of 16. Now let's find out the integer value of the fixed point FC. The calculation is shown here. The integer IC equals the 64-bit product shift right by 16-bit. This means that the middle 32-bit of the product is what we want. Now let's see how we can implement the fixed point multiplication in assembly. For unsigned fixed point UQ1616, we first use the instruction unsigned multiply long to get a 64-bit product. In this instruction, register R0 and R1 are two input arguments to this function, and each of them holds a 32-bit fixed point number. The product has 64 bits, with the upper word placed in register R3 and the lower word in register R2. Then, we shift left the upper word by 16-bit. This removes the leading 16-bit of the product. Next, we shift right the lower word by 16-bit. This removes the trailing 16-bit of the product. Finally, we combine the upper and the lower word into a single register by using the bitwise OR instruction. The final result is placed in register R0, and it holds the lower 16-bit of the integer part and the upper 16-bit of the fractional part. For assigned fixed point multiplication, the process is the same, except that we need to replace the instruction unsigned multiply long with the signed multiply long. Now, let's look at fixed point division. Suppose we are dividing fixed point FA by FB. Assume that they are in the same format of UQ1616. Before the division, we need to shift the 32-bit integer IA left by 16-bit. Because a register can only hold 32-bit, we need two registers to hold the shifted result. In addition, the leading 16-bit are extended by the sign of FA. Then, we divide the sign extended 64-bit dividend by the integer IB. The 32-bit quotient is what we want. Here is the math behind it. As discussed previously, a fixed point number equals the corresponding integer divided by 2 to the power of 16. Accordingly, the integer IC can be calculated in this way. As you can see from the final result here, we need to shift IA left by 16-bit and then divided by IB. Here is the assembly implementation of dividing two 32-bit fixed point numbers. These assembly instructions extend both IA and IB into 64-bit signed integers. In addition, it also shifts IA left by 16-bit. Because we don't have assembly instruction that makes 64-bit division, we need to use a software library function to divide two 64-bit integers. The library implementation is not present here. Thank you for watching. Please visit the book website for more examples. See you next time.